All right, so review from Chem 101, we want to talk about transfer of electrons. So what we're talking about here is oxidation states / numbers. And remember the definition of this is the kind of hypothetical charge on an atom if all of the bonds were ionic. So some bonds will be ionic, so that'll be straightforward. Other ones we're going to just pretend they're ionic to figure out the oxidation state. So let's review some rules for assigning oxidation states. Remember that pure elements and diatomic gases have an oxidation state of 0. So for example, if you had solid copper, its oxidation state would be 0. And all of the diatomic gases, H2, N2, O2, F2, Cl2, Br2, and I2 also have an oxidation state of 0. If your atom has a charge, then that charge is equal to its oxidation state. So charge of monoatomic ion is its oxidation state. So for example, if you have sodium plus, that oxidation state is +1, chloride minus, that oxidation state is -1, magnesium 2 plus, that oxidation state is 2 plus. Third rule is that the sum of the oxidation states is equal to the charge of the molecule. So for example, sodium chloride, you see there's no charge indicated. So when there's no charge indicated, that means that the overall charge is 0. So these oxidation states must add up to be 0. And then think back through Chem 101, sodium is a group 1 metal, so it's always going to be +1. And then chloride is a halogen. It's most of the time is going to be -1. So +1 added to -1 is equal to 0. Another example, nitrate. We see that its charge is -1. And so all of these oxidation states are equal to -1. Think about what nitrogen can be. Nitrogen can have a bunch of different oxidation states, so you don't really know. Oxygen, think about what that is. Most of the time, oxygen is -2. There's 3 of them. And so that's a total of -6 coming from the oxygens. So what must nitrogen be to be an overall charge of -1? Well, nitrogen must be +5. Remember, for our case, metals are always positive. Everything in group 1 will always be +1, right? So that's your sodium, lithium, potassium, that kind of stuff. The alkali metals, everything in group 2, the alkali earth metals, so your calcium, magnesium, beryllium, they're always going to be +2. And then aluminum is going to be +3 all of the time. The post-transition metals get a little bit more confusing. So the post-transition metals can do one of two things. They can either lose all of their valence electrons or just the p electrons. So you can take a look at the periodic table. I like to go to pt2.com. Your post-transition metals are all of these metals down here that are still metals, but they come after the transition metals. And so if you use this pt2.com and you hit this orbitals button, orbitals tab on the top, you can see that there's some numbers under all of these elements. These numbers are their common oxidation states. And so for example, if you take a look at lead, it's +2 and +4. Think about what those charges mean. +2 is losing both of these p electrons. +4 is losing all valence electrons. So these two p electrons, remember f and d electrons are not valence, and then the two s electrons for a total of +4. Bismuth is just normally +3. That's just losing the p electrons. See, thallium can lose its p electron to get +1, or it can lose all valence electrons to get to +3. And then finally, transition metals, we're just going to say that they're positive and variable. right? You got to use other context clues to figure out their oxidation states. And then finally, we have nonmetals. Nonmetals have variable charge, but in general, they want to have a filled octet. So either gain enough electrons to have an octet or lose all of their valence electrons to have a filled shell. So for example, let's take a look at nitrogen. It can be -3, +3, or +5. If you're thinking of -3, that's 1, 2, 3. It's got a filled octet. If you're thinking about +3, that's losing all of the p electrons. And then if you're thinking about +5, that's losing all valence electrons. So 1, 2, 3, 4, 5. In general, there are some kind of rules of thumb, though. Oxygen, being very electronegative, is almost always -2, except with fluorine, right? Think about electronegativity. Last semester, you guys memorized a lot of these things, but now you should really be getting to understand the why behind them all. So fluorine's more electronegative. So if you have OF2, this oxygen is actually +2. And then the other exception is with peroxides. So peroxides are oxygens connected to each other, and then there's other stuff on either end. In this case, they're both -1 each. But in terms of this class, oxygen will almost always be +2, or -2. Hydrogen is a little bit special. It can be plus or -1. It's +1 with nonmetals, because nonmetals are more electronegative, so they take that electron away from the hydrogen, or -1 with metals, because metals are less electronegative, and so hydrogen is actually more electronegative, so it takes that electron. And then finally, halogens, right? So your chlorine, bromine, and iodide are always -1. Fluorine is always -1. The other halogens are -1, except with oxygen. So you guys are advanced enough that you should be able to explain kind of almost all of these oxidation states that you find on pt2.com through the use of having a filled octet or kind of electronegativity type of stuff.